The next speaker is Professor Robert Denk from University of Constance. And the title of his talk is Maximal Regularity and the Newton Polygon Approach. So please.
Thank you very much. Welcome everybody. Good evening, everybody. And so I'm now at the last part of my talk on maximal regularity. So let me summarize a little bit. So in the first part, I explained a kind of machinery called maximal LP regularity to solve quasi-linear parabolic boundary value problems. And this was based on the Fourier multiplier approach, on R boundedness. And you have seen that standard parabolic boundary value problems satisfy these conditions. And to see this, we have described a little bit in detail the solution operators. And in fact, we could gain maximal regularity, which means in the sense of maximal regularity for a closed operator, but we could even obtain maximal regularity with inhomogeneous boundary conditions. Then we are a little bit outside the operator setting. And we considered maximal regularity as an isomorphism of appropriate Sobolev spaces in time and space. And in the second part, I explained a small extension of this machinery, which is suitable if we have a non-standard boundary value problem, in particular if we have a dynamic boundary condition. And then the main idea is we reduce everything to the boundary and we obtain what is called a Lopatinsky matrix. And then to analyze this Lopatinsky matrix and to find spaces where this induces an isomorphism, we use the method of the Newton polygon. And today I will come to some applications. And so the first application will be the Chevron problem, which was also the motivation yesterday. Then I will come to a fluid structure interaction model. And here I'm very happy that Mats Kiet is also a speaker in this conference, who is a specialist in this. And in fact, I can use many of his ideas in this part. And maybe finally, I will say some words on a so-called spin coating process. Okay, so let me recall what the Chevron problem looked like. So we had this form of equation here. So we had the heat equation in the interior, so not Stokes, but heat. But then we had two boundary conditions. So this is already the linearized model, and in the model, the linearized problem in the model problem situation. So this is in the half space. So we have two boundary conditions, and where there appear two functions, of course, u, which is the temperature in the Chevron problem, and the sigma, which describes locally the boundary as the graph of the function. So this is the function. Yeah? And we have seen that we have seen how to reduce this to the boundary, how to compute the Lopatinsky matrix. Yeah? And here I will assume zero boundary conditions just for simplicity. Of course, we can have non-zero initial conditions. We can have non-zero initial conditions, and then we have to use the trace spaces, as I explained, time traces, and we can obtain maximal regularity, including non-zero initial conditions for u and sigma. Okay, and now we want to apply this Newton polygon method, and as I said, this lives on the boundary. And in the final result yesterday of the Newton polygon method, we had an isomorphism. So the Lopatinsky matrix was an isomorphism, but there was a large possibility to choose the spaces, in particular the scales. So we had Besov scale, Bessel potential scale, Triboli-Sorkin scale. And we can also choose the parameters. So we have to decide or find what is the basic space, what is the space where we want to have an isomorphism. And this condition comes from the equation in the interior. So let me start with the right-hand side. And so I'm considering maximal LP regularity, and therefore the basic space for the right-hand side is LP in T and X. So this is my choice now. I could also consider Hölder spaces, but the topic of my talk is maximal LP regularity. And then we have the natural solution space, the parabolic solution space for U. which means that I have a first order in time and I have second order in space. And this 0 here means I have 0 initial values. So everything now has 0 initial values. So this is the solution space I would like to have for U, because it's the solution of the heat equation. And this space for U gives me now the space for G and H in this equation. So because you can see here, we have U on the boundary should be in the same, and the normal derivative of U on the boundary should be the same as the space in the same space as H. So the space for the right-hand side on the boundary are determined by my solution in the interior. Okay. So I've written down here the equation again. And now we can consider the spaces for the space for G, for instance. So G should be the boundary trace space of my solution space. So what I obtain is a Bezoff space, and I lose 1 over P because I go to the boundary. So originally I had the order 2, but now I have 2 minus 1 over P with respect to X. And by some kind of homogeneity, I have, instead of 1, I have going to the boundary, I have 1 minus 1 over 2p with respect to time. So this is the natural space for U on the boundary, for the trace of U on the boundary. And this is my space for the right-hand side G. And similarly, if I want to compute the space for H, then it should be the same as the normal derivative of U. So I have here, instead of a 2, I have a 1. And here, instead of a 1, I have a 1/2. So I have 1 space regularity and 1/2 time regularity less. And this gives me the natural space for H. And so now I have fixed the spaces for the right-hand side on the boundary. And this means I have fixed it in 2 ways. I've also fixed the scales. So I'm here in the Bezoff scale, the Sobolev-Slobodetsky scale. And this will be my choice now for the application of this main theorem from last time, where I have an isomorphism. So I have here this combination of scales. And I will try to apply this Newton polygon method such that it's an isomorphism where G and H are in these spaces. And before I can apply the Newton polygon method, of course, we have to check if the condition is satisfied, this parabolicity condition. Okay, and now I repeat a little bit. So this is the Lopatinsky matrix is a mixed order system, and n parabolicity was defined as n parabolicity of the determinant. And the determinant was given by this expression. And n parabolicity was defined as some estimate on the symbol, but then we have found a much better way to check it. We take the principal symbols, and they have to be different from 0. But there is not only one different symbol, but many different symbols depending on the weight I give to lambda with respect to psi. So the weight means that lambda should have the order gamma compared to psi prime. And depending on the gamma I choose, I obtain a different symbol. So let me, for instance, consider this case here. This case gamma equal 4. So then we omit lower order terms. So we have the square root psi prime plus lambda. And so lambda has order 4 now, but psi prime squared has only order 2. So omitting the lower order term means this is just square root of lambda. And altogether, I get for this, the principal part is the first part, which has order 4, plus psi prime squared times square root of lambda, and the order of all this is 4. And this gives me for this principal part. And I do this with all weights. It's easily seen that there are only finitely many possible results for the principal symbol. And you can see this list of principal symbols here. And now we have to remember the condition of n parabolicity means that whenever I take a psi prime, which is different from 0 in Rn minus 1, and a lambda in the right half complex plane, which is different from 0, then this principal part should be different from 0. And now this is trivial here. Yeah, you see here, for instance, this is different from 0. This lambda is different from 0. Of course, also this is different from 0. So just by looking on these principal symbols, we immediately see that all these principal symbols satisfy these conditions. Okay, and this means that our Lopatinsky matrix is n parabolic. And this means that we can apply the main theorem, which tells us now that this mixed order system gives an isomorphism in some spaces, and the spaces are defined by the structure of the matrix and the corresponding Newton polygon. Yeah, and if you compute this for the Chevron problem, then you obtain the Newton polygon space for this function sigma. Yeah? So this in some sense correct space for this sigma, which describes locally the boundary as a graph, is an intersection of three spaces. So we have order 3/2 minus 1 over 2p in time with LP in space. Then we have some mixed space, 1 minus 1 over 2p and second order in space. And then we have LP in time and order 4 minus 1 over p in space. And I have written here the Newton polygon corresponding to this. So this space is defined by the Newton polygon. So for instance, this point here is of order 0 in time and of order 4 minus 1 over p in space. So this corresponds to this. And as we said, to every vertex of the Newton polygon, I have such a space, and the complete space for the complete Newton polygon is the intersection. And you can also see geometrically here that we have this. The important thing is this vertex here. So this vertex is a dominating mixed smoothness. It cannot be obtained by some mixed derivative theorem applied to the other two vertices. So this is a dominating mixed smoothness, and therefore it's necessary to have this intermediate space included. Okay, so this is what the Newton polygon method tells me, that this is the space. So it determines the space and says in these spaces defined by the Newton polygon, this is an isomorphism. So we can apply the result, and I formulate it in this way. So T is always finite in my talks, and it says it induces an isomorphism. So the Lopatinsky matrix, which is defined here. And now I replace the symbol by the operator. So I have a matrix pseudo-differential mixed order system, dx prime and dt. But this induces an isomorphism in the spaces just defined. These were the spaces for the right-hand side, the trace space for U, and this space for sigma. It's an isomorphism. And this is the Newton polygon method. You check these conditions and then you obtain the isomorphism, choosing the scales in an appropriate way. And now we know this is an isomorphism. So given the right-hand side, G and H, we can compute the inverse. So we can compute the trace of U on the boundary and sigma. And then sigma is already known. And we know the Dirichlet trace on the boundary. But then we can simply solve the Dirichlet problem. It was the heat equation. We solved the heat equation with this given Dirichlet boundary condition. And therefore, we obtain a solution. And then in totally, we obtain the solution space for U, which we want to have, this canonical parabolic space. And we have a unique solution where the sigma is in this Newton polygon space. And this is formulated still in the half space, but then you make a localization and coordinate transform and local coordinate transforms, and you get this also in the domain in the same spaces. So you see here that the Chevron problem for all appropriate initial values has a unique solution in these spaces, where for the temperature we have the space we would like to have, and for the function which describes locally the boundary, we have a somewhat strange space, which is the intersection of three different spaces. And the same result, by the way, was obtained earlier by a paper of Escher, Simonet, but they didn't know the Newton polygon. So they had to calculate these estimates on sigma explicitly, in a very long calculation. But with the Newton polygon, so the Newton polygon method helps us to understand the structure of the equation. So in particular, this Lopatinsky matrix has some hidden inhomogeneous structure. This is this dominating mixed smoothness, which appears when you write down the solution space for maximal regularity. Okay, so this is the Chevron problem, and I can now make some remarks. This was an LP setting. What happens if we consider this an LP-LQ setting? So now I consider LP-LQ setting. P and Q may be different now, everything in the reflexive range. So this is again my choice. So I want to have maximal regularity with the right-hand side in LP in time and LQ in space. And then, of course, we make the same steps again. And then, of course, the space for the solution U is again canonical. It's this typical parabolic solution space, now with P in time and Q in space. And the next step would be to find the spaces for the right-hand side of the boundary conditions. And these are the trace spaces. And it's exactly the trace, taking the trace of this space where now Trebel-Sorkin spaces appear. So it is known that if you take some function u in the solution space and you take the trace on the boundary, then you end up with this intersection where you have here the Trebel-Sorkin space in time, and here you have as before the Bezow space. And the indices, so the differentiability orders, are exactly the same as before. Just the trace result is different. And this means if we apply our Newton polygon method, that now we are changing the scales. We have the scale which is now Bezow in X and Trebel-Sorkin in time. But this was admitted, this was possible. So in the main theorem, we had the choice of scales. So again, the scale I want to have, this isomorphism, is determined because of the trace results. Okay, and now the machinery, of course, works. We already know it's n parabolic. We can apply the main result. And the spaces, of course, for sigma is again, it has the same Newton polygon, but again, of course, it's now a mixture, an intersection where I have Trebel-Sorkin spaces. So I'm in the Trebel-Sorkin scale with respect to T, and I'm here in the Sobolev-Slobodetsky scale with respect to X. So I have either Bessel potential spaces or Bezow spaces if it's non-integer. So here you can see in a natural way, here appear all scales. Bessel potential for integer, Bezow for non-integer Sobolev spaces, and Trebel-Sorkin with respect to time. But the result is exactly the same. So we have for first of all, again, the Lopatinsky matrix induces an isomorphism in these spaces. So this is in some sense the hard part of this result. And this is the Newton polygon method. And then solving the Dirichlet boundary value problem for the heat equation, I obtain my solution U. So I have here, again, the classical solution space, and I have here this strange space for my function describing the boundary. And this result was first obtained, I would say, in the PhD thesis of my PhD student, Mario Kaip. And he had some small restrictions between P and Q, which was based on some technique in the proof. And these restrictions were removed a little bit later by Mairis and Ferrar. So now it's true for all P and Q between 1 and infinity without any additional restrictions. Okay, so this is how to apply the Newton polygon method. And the point I want to emphasize is in the formulation of the Newton polygon method, we have a choice of scales, and the scale should be adapted to the problem where our Lopatinsky matrix comes from. You can see here either Trebel-Sorkin or Bezow spaces, depending if we are interested in LP-LQ or only LP maximal regularity. Okay. So I come to the second application, the fluid structure interaction model, and this was published in a paper jointly with Jürgen Saal last year. And now I'm very happy because almost everything was said by Mats Kiert in his very nice presentation. So I can refer to him. In fact, we consider the same equation, almost the same equation, and we come to almost the same results. This is very interesting, and we need to compare our methods and results. And so the hard analysis was explained already in the talk of Mats, and therefore I have now some glasses on the Newton polygon glasses. So I look to this equation with my Newton polygon filter.
Excuse me,
Okay.
there is a question from Professor Shibata.
Yes.
I'm sorry, I disturbed you a little bit. Just ask you some of the Stefan problem. I mean, I'm interested in formulation of equation in more semi-group setting. Meaning is that sigma t is also I want to consider the evolution equation, right?
Yes.
That case is also so. This means that I don't want to have some of the resolution space. So I don't know, F instead of F, if you put H1P and then also LP, then is it possible or not?
On the boundary?
On the boundary. I mean, you take the boundary place,
Yeah.
but maybe
Yeah. Okay.
it's not okay. So don't take a boundary trace, just something. I mean, evolution equation, like H1. It's possible.
Okay. So first of all, I should mention that out of this, so this maximal regularity is in some sense, say, optimal because it's simply an isomorphism. But out of this maximal regularity, you obtain, as you said, an evolution. You can write it as a semigroup. You obtain a semigroup which has maximal regularity, which lives in the product space of the interior and on the boundary. This is an immediate consequence of this maximal regularity theorem. You can define appropriate space on the boundary and in the interior such that you get an analytic semigroup, which additionally has maximal regularity. But this follows from this theorem.
Okay.
Yeah.
So, but in that case,
I would like to say that I like the spaces on the boundary. If you take the evolution on the boundary, then you should live in the boundary trace spaces.
Okay. Thank you.
So from my point of view, triplet Sorkin here is not a mistake. So or not so bad. Yeah.
Yes.
Okay.
Okay. No, I never.
But you're right. One obtains analytic semigroup. With respect to U and sigma, because it's an evolution equation in U and sigma simultaneously. You're completely right.
Okay. Thank you.
Okay. Okay, so this is the situation, and in the fluid structure interaction model, so I have the Navier-Stokes equation, I have some fluid, I have some elastic plate, and it's exactly the same equation as Mats Kiert had. I do not consider the periodic setting, neither in time nor in space. So I consider an even simpler situation in space. I consider the half space situation. And you have seen in the talk of Mats Kiert already that this is the simplest case in some sense. But the analysis, of course, on the torus is more or less exactly the same as in Rn. Okay, and I have here the model again, which is more or less exactly the model Mats Kiert had. So I can make this very brief. So I have that u is this is the velocity of the boundary, which is assumed to be in vertical direction only. This is a classical plate model. And this means no slip boundary conditions because the velocity sticks to the boundary. And here we have this equality of the forces. So we have this coming from the fluid. So this is the damping term coming from the fluid. And this is now hidden. This is the elastic plate. This I will write down in a minute. And it's a standard Navier-Stokes system. So I have the standard stress tensor with a symmetric gradient. and I have an incompressible fluid. So it's exactly the same equation. And if I'm not wrong, maybe there was some small difference here. And this is not our model, and I'm not a specialist in modeling. And I have to say, I completely agree to Mats Kiert that I'm not so convinced about this Kirchhoff plate model. It's not coming from physics. And in particular, this Kirchhoff plate model assumes that the forces are going only in vertical direction and not in normal direction. And this is, you also have to be a little bit careful, because the Navier-Stokes equation here is written in Eulerian coordinates, whereas the plate equation is written in Lagrangian coordinates. But this simply means that you have to be a little bit careful. Okay. So again, this is the equation. And in the same way as Mats did this in his talk, I assume that I have a Kirchhoff plate model. So I have here second order in time. I have here the typical B Laplacian, and in particular, I have here this strong damping, which is, by the way, also known, at least to me, as a structural damping. Structural damping. And as was mentioned already, this damping term makes this plate equation a parabolic equation. So I am coupling a parabolic, the parabolic Navier-Stokes equation with a parabolic plate equation, and this is why we should expect maximal LP regularity. Okay, and of course, as already Mats said, the main task would be to omit this damping. So the question is, what happens for gamma to 0? And we cannot answer this question. So we are just at the beginning, and it will be a pleasure also to discuss with Mats on this approach. So hopefully we will have some joint cooperation in this direction. So let me give some references. So this fluid structure interaction in this form was applied to cardiovascular systems, and then it was analyzed from a mathematical point of view, mostly in L2, by, for instance, Pada Takahashi, generation of an analytic semigroup. A little bit earlier, we had by Grammont a strong solution in L2, and there is a whole group which considers weak solutions. And in the weak setting, in the weak L2 setting, they are also able to include this parabolic hyperbolic setting, which I cannot do. And as has become very clear in the talk of Mats Kiert, I also do not expect LP theory hold in the hyperbolic parabolic setting. So this is, as he also already said, due to the fact that dispersive equations, there's no LP theory for dispersive equations due to some results by Leon Hermander. Okay, and now a little bit, there are also several results, for instance, by Galdi and Kiert on strong solutions. And it turns out that very recently, so more or less last year or the year before, several groups worked independently on maximal LP regularity. And one is, of course, Mats Kiert, as you have seen in his talks. And the other is also Mighty Takahashi, which also obtained maximal LP regularity. So these approaches were developed in parallel. And so these are, to my knowledge, the first papers which deal with maximal LP regularity in this setting. Okay, and I start with the main result. So, so first of all, let me start with the standard spaces. So for the velocity. I'm sorry, here in my result, U describes the velocity of the fluid. I was too lazy to change the notation, and eta describes the boundary. So I'm sorry for this. So this is the function, the boundary is given as a graph of a function eta, and eta is in some sense the interesting thing. So U is the velocity of the fluid, which is in the standard space. It's a free boundary value problem, of course. So we have a variable domain, time-dependent domain, and Q is in the homogeneous first-order Sobolev space with respect to x and no smoothness in time. It's just LP. So these are the standard spaces for Navier-Stokes equations. And at least in my result, I have as before in the Chevron problem, I have the intersection of three spaces for eta, which describes the boundary. And I have here in x, with respect to x, I have the differentiability 5 minus 1 over p. And then I have this mixed term. I have a second order in time and 1 minus 1 over p in space. And these two spaces are exactly the same as Mads had in his talk. But we have an additional, a little bit more regularity in t. That's a little bit larger than 2 here. So we have an intersection of three spaces. And you can guess, so this intersection, of course, comes from the Newton polygon method. Okay. Of course, we have to know something about the initial values at time t equals 0. And we have the standard initial value for the velocity of the fluid. This is in the Bezoff space for the 2 minus 2 over p. And then we have for this function describing the boundary. So we had this eta, which describes the boundary at time t. We have a high regularity, as we have already learned in the talk before. We have high regularity, and therefore we need more. And we have a second order in time equation, because it's the plate equation, which has dt squared. So we need two initial values. And it turns out that the appropriate initial values should belong to this Sobolev space of order 5 minus 3 over p and 3 minus 3 over p. And as always, these initial values are the result of trace theorems. Yeah? We know the space for eta, at least the space we want to prove. And then we have to take these functions at time t equals 0. So we need results on the trace of Newton polygon spaces. Eta belongs to some Newton polygon space. And then we have to know what happens if t equals 0. Yeah? But these results are available due to some paper with Jürgen Sahle and Jörg Seiler. Yeah? So this is known, and the result tells us that these Bezoff spaces are the appropriate initial values for the initial domain and for the initial velocity. Okay. And then the main result tells us that in these spaces, we have a unique solution, or more precisely, I have n is greater or equal to 2, p is greater or equal to n plus 2 over 3, finite time, I fixed the time, which is arbitrary but finite. And then there exists some constants kappa, such that for all initial values in these spaces, satisfying appropriate compatibility conditions, which are small. So I have small initial data, then we have a unique solution of the fluid structure interaction system, and it's still in the graph. It's still the graph of a function, and the function has this smoothness in the function space described before. Okay, so this is our main result on the nonlinear problem. So I formulated it now in the way that we have an arbitrary finite time interval, then we get for small data a unique solution. One can also get a short time solution for arbitrary data, but this is not what I want to present. Interesting may be the situation p equal 2, because of this condition. If you check this in the physical relevant cases n and equal 2 and 3, then p equal 2 is included. And in this situation, this is interesting because if you want to go to a singular limit from the parabolic to the hyperbolic setting, so maybe the case p equal 2 is important, and it's not so bad to have maximal L2 regularity here. But this is for the future, I would say. Okay, and the steps we do to prove this is now this standard machinery, the standard program. So we take a Hans-Sava transform, we transform it to a fixed domain. And here we have not been as clever as Mads in his talk. So we take the straightforward transform, where our theta maps tx prime and xn to tx prime and xn plus eta. You see, if xn equals 0, then I'm exactly on the boundary of my variable domain. So this is the naive approach to a transformation. And then we plug this transformation in and obtain, we take the push forward of our u and q, and we obtain now an equation in v and p, which is of course nonlinear, which has several nonlinearities. And so we obtain this system in the fixed domain now. And note that the fixed domain, I had no bottom here. So the original equation was already some bent half space, so I have no bottom here. So I'm here already in the half space. So I don't have to care about these localization problems Mats told us in the talk before. Okay. And what is interesting here is that the linearization looks a little bit different. So we have this additional term here, and I don't know why. So either this was a mistake in our calculations, or it comes from the slightly different model. I have the impression that we had the stress, the damping of the fluid was in our model a little bit different. So this is additional here. And maybe this also makes a difference in the result. This I cannot check. Okay, but now we are in the setting we are very familiar with. We have a quasi-linear complicated boundary value problem in the half space. So we take the maximal regularity approach. We write all nonlinear terms to the right-hand side, and we solve the linearized problem. We prove maximal regularity, and we have a fixed point iteration for small data. We obtain a unique solution. So this is exactly the machinery which I told you in my talks, and which is the standard machinery now. Okay, so I repeat, this is just the same equation, and I want to take a look to the nonlinearities. So I have written them down here. So the nonlinearities are, many of them are quadratic. For instance, we have here this quadratic term dt eta dnv. Some of them are cubic linearities. Yeah? So we have many nonlinearities appearing from this transformation, of course. And one important step in proving unique existence for the nonlinear problem is embedding. So we have to guarantee that these nonlinearities are in our maximal regularity space. Yeah? In particular, for instance, for this f here, I want to have it in LP. Yeah? 0t LP Rn plus. Yeah? So we have to guarantee in this iteration process, or in this fixed point argument, we have to guarantee that all this belongs to this space. So the first part is the linear problem. The second part is embedding for the nonlinearities. Okay. So I now have the linearized problem. So the only difference to the slide before is that I have here replaced the right-hand side by some fixed functions. And I have chosen the appropriate function spaces. For instance, of course, here we have LP. I consider here only LP theory. And for the right-hand side of the divergence, I have also a classical space. It's HP1 in X, in LP in time. And we have additionally this space here. And for the first H, I have this space. Yeah? So these are the spaces. And as in the Chevron problem, so thinking of the Newton polygon approach, these spaces define the right-hand side. And now I have to check if I can define a Lopatinsky matrix such that I get an isomorphism to appropriate spaces. Okay. And the result is as you expect. So we have this linearized problem has a unique solution if and only if these data belong to the spaces above and satisfy the compatibility conditions, which I do not want to write down here. And in particular, you can see here that here this space appears, which already appeared in the main theory. Yeah, it's always the same. We prove maximal regularity for the linearized problem in some spaces, then we get a unique solution for the nonlinear problem in the same spaces. Okay. And now I'm very happy that the talk of Mats Kiert was exactly before my talk, because he did exactly this computation, which describes now I'm making the standard machinery. I take Laplace transform in time, partial Fourier transform in space, and then we, on a symbolic level, we obtain this relation, which was more or less exactly the same, maybe some small differences, like the relation Mats Kiert had in his analysis. Yeah? And so we can solve the equation for the pressure explicitly on the symbol level. We plug this in, and then we obtain, recall that this is what was called U hat in the talk before. Yeah? And we have here the symbol in the denominator, we have the symbol of the Laplacian, Laplace-Beltrami operator. But here we have some more complicated expression, and I've written it down here. So essentially we have this is the symbol of my plate. This corresponds to the plate equation. We have second time derivative, B Laplace operator, and our strong damping. And this is, by the way, always a lower order term. And so this symbol of the plate operator is multiplied by psi prime squared. And then additionally, we have this part where we have this typical omega. So this omega is the square root of lambda plus psi prime squared. And we have seen this many times already. This always comes from just solving the equation in the interior, as in the Chevron problem, and then taking the normal derivative, and this corresponds to the normal derivative on this level. Yeah? And here we have a complicated expression. You have lambda, omega squared, and this. So this is our result. And once we know eta, by the way, we are done. Because I go back a little bit to the equation, because then I can simply consider this part, which is now the Dirichlet problem for the Stokes equation, if we know eta. So the task is to compute eta. And therefore, we made it in this way, that we explicitly calculated a formula for eta, and then and we have this formula. And now we have to understand, we want to replace, of course, the symbolic level by an operator. We want to plug in dt and the negative, the square root of the negative Laplace Beltrami operator, and we need mapping properties. Yeah? So we know the space for H, we want to have the space for eta. And of course, now we are in the Newton polygon machinery. Yeah? So this is a complicated expression in lambda and psi prime, a complicated operator in dt and dx. But now we have this machinery. We can, as I told you yesterday, we can define this operator by a joint H infinity calculus or by Fourier multiplier methods. And then we can check if the Newton polygon method holds, can be applied. And this is now our symbol. Yeah? So I replaced psi prime, modulus of psi prime by z. Yeah? So we have here again this m coming from the plate equation. And what we do in Newton polygon machinery, we draw the Newton polygon of this function. It's a complicated function, but you can easily see, for instance, we have here z square, and here z to the 4. And in this combination, this gives us this point here. And you can also see here we have lambda, another lambda, a square root of lambda. This gives us this point. So this symbol, which is the solution operator, has a Newton polygon. And now we can apply this machinery. It's a scalar equation here. It's a little bit easier. And we know that it's an isomorphism. We have to check, of course, if it's parabolic in the new sense. And again, we go to the principal parts. So in the same way as before, we go to the principal parts, and this is something I want to omit now, but you can easily compute the principal parts. For instance, if the weight of the lambda is very low, then this is the principal part. All lambda is then lower order. And you can easily check, very similar to the Chevron problem, that all these principal symbols are different from 0. So it's n parabolic, so we are in business. Okay. And then we get the following result. So we just study this NL. Yeah? So the operator related to the symbol is an isomorphism from some Newton polygon space to the basic space, which is of order 0. And then this space is defined as intersection of these spaces because it's a Newton polygon. Yeah? Okay. And note that here I'm not LP setting, but I have chosen here the Bezoff scale. And this is due to the fact that everything lives on the boundary, and in the end, I have Bezoff scale in my boundary. I want to have the Bezoff scale because they are the boundary values of my velocity u. Okay, and this isomorphism gives us essentially that if we define eta by this solution formula, where now I plugged in the operators instead of the symbols, then this is in fact in my solution space for eta, and this strange Newton polygon space. Okay, and this is the key step for maximal regularity for the linear problem. Okay, so we get an isomorphism, and the spaces are described by the Newton polygon. Okay, and now the second part is now to study the nonlinear system. So I go back to the nonlinear system where I have here the nonlinearities. And by construction, the value and the Fréchet derivative of the right-hand side is 0 because all linear parts are on the left-hand side. And so we have essentially we have to guarantee that they are in the correct, these right-hand sides are in the correct spaces. And I want to make this in one example. So this is one example we had before. So we had this product on the right-hand side. We had this product of dt eta and dnv. V was the velocity of the fluid, and we want to have it in LP. Okay, so we now we need embeddings. So first of all, eta was in a complicated Newton polygon space, but we use some embedding here, so we can embed. We know eta is also, as a consequence of this, it's also in this space here. And now, if we take dt eta, we obtain also some more standard space, and which I will now write for some reason as an anisotropic Bezoff space. So the first component here in my product belongs to some anisotropic Bezoff space, where we have the weight 2 and 1. So the time derivative here is always half of the order of the time derivative here. It's always half of the order of the space derivative. This is an anisotropic space where the time has weight 2. Okay, this was the first component, and in the same way, we know, of course, the solution space for our velocity. So this is this space. And this is, of course, also an anisotropic Sobolev space. Here we have, again, this parabolic scaling, t with respect to x. So our velocity belongs to this anisotropic space. And now I reformulated our two factors as belonging to some anisotropic spaces. And why did I do this? Because now we can apply a black box which tells us that the product embeddings for products of such anisotropic Sobolev spaces. If you have two components, the first one belongs to this space, the second to this space, then this is embedded, continuously embedded in this space, which is nothing because order is 0, which is nothing than LP. And such, so I just wanted to tell you that we need such embeddings. And such embeddings could be found, for instance, in a paper by Kühne and Saal, where you can simply read off the indices and then show that this embedding holds. But this guarantees that this product belongs to LP, and the maximal regularity machinery works. So I summarize, again, I state the main result. We have a unique solution in the canonical spaces, except for eta, where we have this Newton polygon space here. So it's the intersection of 3 spaces. And the main ingredients are the Newton polygon method for the linearization and embeddings for the nonlinear part. So this is just a scheme where one can treat many boundary value problems. And the last example I want to present you is the so-called spin coating process. It's very similar. And this is a joint paper with guys at Heber, Saal, and Zawada. And spin coating means I have a fluid which is put on some disk, and this disk is now rotating. So I have a fixed lower boundary, and I have, so this is a fixed boundary. I have here again a free boundary, and I have the fluid, and I have the Navier-Stokes equation, and now I have forces. I have on the surface, I have a surface tension in my model. So everything is very similar to before, and I go to the equations. I just write down the main equations. So I have again the Navier-Stokes equation, the standard Navier-Stokes equation, but then I have here some rotational force, Coriolis forces. So this is rotational forces. I don't want to describe all expressions in detail. So essentially, this is the model for the Coriolis forces. I again assume that I have incompressible fluid, and here I have a surface tension. So this is the surface tension on the free boundary. On the lower fixed boundary, we assume Navier slip conditions. Of course, we need some initial values and so on. And this, as before, gives the dynamic behavior of the boundary. So the normal velocity should be the normal velocity of u. So this is the dynamics of the unknown boundary. Okay, and now the same machinery is starting to run again. So I can transform it locally to a fixed domain. Then I obtain a quasi-linear equation. I consider its linearization. And then I consider the Lopatinsky matrix. And in my example here, this is the Lopatinsky matrix of the whole system on the boundary. And you can see here the typical ingredients. So we have, again, this omega coming from the Stokes equation here in several places. And I also have Xi1, Xi2, and I also have the Laplace-Beltrami coming from the surface tension. So this is maybe incredibly or somehow complicated metrics, but our machinery does not care about it's complicated or not. We can compute a determinant, we can check if it's n parabolic, and we can check if it has a Newton polygon, and in fact it has. So this 5x5 Lopatinsky matrix has this Newton polygon. And once we know this, we are in some sense happy, because then we know the spaces. We can check if it's really n parabolic, which is the case, which is also very easy again. And then we obtain that this Lopatinsky matrix induces an isomorphism in the appropriate spaces, which are complicated spaces. And at the end, we obtain the following result for the whole system. So we have, for sufficiently small time, it's again a local in time result. We have the velocity of the fluid in the standard space, the pressure in the standard space, and the function which describes the boundary in, again, a non-standard space, which is a Newton polygon space, which is described by this Newton polygon. And we get the fact that we get an isomorphism for that the Lopatinsky matrix induces an isomorphism means that we can reduce our very complicated boundary conditions to standard Dirichlet boundary conditions, and then we can, of course, solve the Stokes equation with standard Dirichlet boundary conditions. Okay, so you can see the scheme, I guess. You can see the machinery. And it turned out to be useful in many situations, and this is now my final remark. There are other applications, and for instance, I would like to mention here the plate equations. So not a fluid structure interaction, no fluid, just a thermoelastic plate equation, which is itself a mixed order system. And this is something you can analyze with a Newton polygon. I would also like to mention here B Laplacian with Wenzel boundary conditions, which is an ongoing work with Kunze and Ploss. And Wenzel boundary conditions mean you have B Laplacian, so the plate equation is Laplace squared, and Wenzel boundary condition means you have the Laplace squared on the boundary. And this falls out of the canonical scheme because the order of the boundary operators is too high. Yeah? And this is also related to dynamic boundary conditions, so this is similar. Or where you also have dynamic boundary conditions, Cahn-Hilliard equation. Or going to fluid mechanics, we can consider the generalized LP-LQ Stokes problem. We can, as you have already seen, maybe you can consider the Navier-Stokes equation with surface tension and gravity. And we can also include some viscosity on the surface. Then you get a two-phase Navier-Stokes equation with business-driven surface fluid. And all these, I have given here some references. All these equations were treated by some people in an explicit way. Yeah? But all these equations have some hidden Newton polygon structure. And in all these equations, you can prove that the Lopatinsky matrix, which can be computed here, is n parabolic and induces an isomorphism, which then gives the spaces and maximal regularity in these spaces for all these equations. Okay, so this is just a remark or some applications. So the main applications are, of course, fluid mechanics, dynamic boundary conditions, or let me say non-standard boundary conditions, like the Wenzel boundary conditions, or like in the thermoelectric plate equation, mixed order systems, when you already start with a mixed order system. And this was, by the way, also the motivation for Wolewicz and Gindikin, who invented the Newton polygon method for mixed order system, not on the boundary in the interior of the domain, so in whole space. Okay, so I'm at the end of my 3 talks. I hope you could get some slight idea of a machinery of the Newton polygon. And in my opinion, it can be useful to understand the equation. Yeah? If you have a triangle, you have no Newton polygon, then it's a classical parabolic equation. If you have not a triangle, but a Newton polygon, then it's good to look into this Newton polygon approach. With these remarks, I would like to thank you very much for the attention. Again, thank the organizers for giving me the possibility to speak here. Thank you very much.
Thank you for your very interesting talk. Are there any questions or comments? Also, Professor Terasara, please.
Oh, sorry.
I have a question. So in joint work with the Sal, you treated, so plate equation coupled with Navier-Stokes equation, right?
Yep.
And in your theorem, you get, so for fixed t, if data is small, one can solve until time t, right?
Yes.
But do you get the global existence for small data?
Yeah, this is what you should expect. I have to say, we did not care about this, so we did not check this.
Okay.
But of course, one should get for small data global existence. Yeah.
Okay.
But we were too lazy to check this. Yeah.
Okay. Thank you.
Yeah.
Are there any questions or comments?
I have a question. I cannot figure out the thing with the hand. I'm sorry.
No problem.
Okay, so thank you, Robert, for an excellent talk. I'm very impressed with what you're doing with this Polygon methods. It's really impressive. One question: the BS of space 9b 9/4 or minus 1/4q. Here it is. It's in the. Was this the fluid? Yeah, this is the fluid structure, right?
Yeah. This is yeah.
So
yeah.
Are you sure that this is? Are you sure that this space is in fact smaller than the intersection of the other twos, or could it be that maybe the other, if you take the intersection of the other two spaces, H2P and LP, that
yeah, you can. Yeah, I understand the question. Thank you very much. Yeah, you can see it because this is a time derivative which is larger than 2. If p is larger than 1, then you get something which is larger than 2 in time. And this is, you can also see from the picture. So this is an additional time regularity we get out of the system. So it's not included in the other two spaces. Yeah? You can also see it in the Newton Polygon picture. If I draw this picture correctly, it's not on the edge combining the other 2 points. It's really higher time regularity, additional time regularity we read out of the
yes,
equation.
of course, you have so you get a higher. Yeah, but so you have higher
slightly higher time regularity as the other 2 spaces, which, if I have seen this correctly, are the spaces you had here. Yeah?
Yeah, that's true. Yeah, okay, so they do not, of course, they don't embed. Okay, well, that's very interesting. I need to understand that point. The other question I had was one comment. You mentioned the factor that differed in our talks in the coupling condition. I have to admit, the physics behind this coupling condition, to me, it's it's not clear. So
I fully agree. Yeah, so this is
you have 2 normal vectors. You have one from the reference and one from the, and I think it's a matter of religion whether exactly how to do this, and it's not physically 100%. So
I completely agree. Yeah.
And one question, you mentioned this, the term that I call it Kelvin-Vogt damping. I don't actually know why. I picked that up many years ago. You call it structural damping. I have been looking for some years for a physical justification for this structural damping term. I never found one. Did you find one? Have you heard of?
Yeah, this is also a good question. So I have some other papers on plate equation itself, and this structural damping is really used also by engineers, at least. So structural damping in my theory is take half the time derivative and half of the operator, so the square root of the operator appearing in the equation, and this is really something the engineers use. But again, I never seen a physical reasoning for this. Yeah.
Okay.
So this is also, of course, there are people who know this, but not me. So I don't know. Yeah. So, but I know that it's commonly used. It's really commonly used in plate theory to have this kind of damping, dt Laplace. Yeah. No matter how we call it, dt Laplace. Yeah.
Interesting. And one final question: if I understand correctly, you could take the beta equal to 0. Is that correct? You also mentioned that the term.
There was one lower order term in my equation.
You call it lower order, exactly.
So not I guess this was a term which did not appear in your equation.
Exactly. Yeah.
So where? Sorry for this. Yeah. Okay. So this term, this is exactly the model we took from the references here.
Yeah.
But this is in any way a lower order because we have here dt Laplace, and this is second order in X, so it's dominated by a combination of these 2. Yeah? So this is really lower order. Yeah. And in the Newton polygon, I didn't mention this, in the Newton polygon picture, it's in the interior of the polygon, which means lower order, really. Yeah? It's not on the edge or vertex, but it's in the interior. And this is the case here. And this is really a perturbation argument. Yeah?
You could put it to 0 then, okay? Because
we can put to 0 no matter. Yeah.
Okay, I was just want to be sure. Okay, yeah, I have a lot of questions, but I need to read your paper and then I'll come back to you. Thank you very much.
We will keep in contact. Thank you very much. Yeah.
Yes.
Are there any questions or comments? So I have one question that in your first lecture, you said that the condition on P controls the nonlinear term, which we usually ensures Sobolev embedding. However, your main result obtained with Professor Zhao, your condition on P looks like very slightly wider than the previous lecture.
Yes.
So this means that in this to obtain this theorem, you do not use the Sobolev embedding. Is that correct?
Yes, thank you for this question. Yeah, this is an important point. Yeah, so by standard Sobolev embedding, one would expect larger p, so less possible p, and this is the essential point in this paper I mentioned by Köhne and Saal, that they can improve because they are considering always we have not the simple Sobolev embedding into L infinity, but we have this intersection spaces. Yeah. So they formulated in this in the anisotropic setting. Yeah. So this anisotropic embedding is better than the standard embedding only with respect to x. And this is the key point of their result. Yeah. So they can lower down the border for p. But this is the hard part of their paper. This enables us to go below the standard embedding border.
So you mean considering time and space is essential?
Exactly. Consider time and space simultaneously. All these functions belong to have also some regularity in time, and you must not forget this. And then you get better embeddings than only embedding in space.
Oh, okay.
Yeah.
Thank
And
you very much.
End up with some Hölder function in space.
Are there any questions or comments? So if not the case, let's thank speaker again.